Hello everyone, my name is Ian Kim, and this is my MathQuantum 2026 Symposium recorded talk. This video is on quantum Ramsey theory, van der Waerden's theorem. Last summer, I presented the idea of quantum Ramsey theory in my mini project. After digging into it further, I found that there was actually a lot of contributions done in it already. So I decided to narrow it down to van der Waerden's theorem, van der Waerden's theorem being a corollary of Ramsey theory. So here's our motivator. Ramsey theory essentially argues that if you have a large enough system, like a graph or a set of numbers, you're guaranteed to find a subsystem with a specific property, regardless of how you color, partition, etc. In this presentation, though, there's a bit of a simplified way of saying this. Complete disorder is impossible, or structure is unavoidable. They're basically saying the same thing. Okay, let's take an example here. Let's say we have the integers 1 through 8 in front of us. And we're going to color these integers just randomly. So here's our question here. Can you always find a monochromatic, which means similar color, arithmetic progression of, say, length 3? Arithmetic progression here meaning that you start with a number and then you count up with a similar step size. So for example, 1, 2, 3, which is a length 3 arithmetic progression of step size of 1, or 1, 4, 7, which is a step size of 3. Take a second and think about it. The answer is actually no, you can't. And here is such example where that is not possible. If you look at this here, I mean, you can't have, let's say, like 1, 4, 8. That's not really arithmetic progression. 3, 6, 7. That's not arithmetic progression of red. So it's impossible actually. So it's not guaranteed in this example. So no. But what about 9? What if we add another integer? Would that guarantee our arithmetic progression of length 3 that is monochromatic? The answer is actually yes, it is. And this is where we segue to van der Waerden's theorem. Van der Waerden's theorem states that for any given positive integers, r and k, there is some number n, such that if the integers 1 through n are colored, each with one of r different colors, then there are at least k integers in arithmetic progression whose elements are of the same color. The least such n is the van der Waerden number, w of r of k. So we prove that w at 2 or 3 is 9. And if we take the example from earlier, if we add a red 9 at the end, then 3, 6, 9 is arithmetic progression, and 1, 5, 9 is also arithmetic progression. That's a similar color. Great. Let's take some key ideas here. So this theorem guarantees that structure exists. However, it doesn't really tell you exactly where. And that's the biggest issue. You can randomly color as many as you want, as many 1 through 9s as you want. But you have to test every single one of them just to show that it's all guaranteed. Well, I don't think so. That's a lot of work. So that's a big issue. This classical proof is combinatorial. We have double induction on variables k and r. It's not really constructive. Van der Waerden's numbers grow enormously fast. For example, w of 2 of 6 is literally 1132, which is actually important for the quantum motivation, as you can deal with bigger numbers with quantum. So basically what this is saying is that, yeah, the theorem is existential, but we can't really know where it is. There's no witness of such example existing. So let's go quantum here. Here's a key idea. Instead of checking colorings one by one, which is just classical, we can use quantum superposition to examine all colorings simultaneously. How do we do that? So here's our first step. Let's say we have n qubits, and like we established being the least, right? Placed in a superposition of all 2 to the n colorings at once. Makes sense because they can be either red or blue. So hence the 2 to the n. And we actually apply Hadamard gates, which are age gates on each. This is the mathematical expression of it, and this is the circuit symbol. The H gate is actually one of the things MathQuantum taught me last summer, and what it basically means is that it's the gate that transforms definite states into superposition states, and vice versa. Our second step is that we define a quantum oracle, and this is known as the black box a lot, or O. They call it that because you just insert something in, and you don't know what's really going on in there in the function, but you get some output though. And that marks colorings containing a monochromatic arithmetic progression of length k. So here's our quantum oracle. This definition, O ket x equals -1 to the f of x times ket x, where f of x is 1 if x contains such an arithmetic progression. And this is the circuit symbol. Notice how the gate is slightly elongated vertically since many qubits run through it in the circuit. So what does this all mean in context? And how do we connect it back to Van der Waerden's theorem? Van der Waerden says that f of x equals 1 for all x when n is greater than or equal to Van der Waerden of Rk. So what this basically means, in other words, is that every computational basis state ket x satisfies f of x equals 1. This means the oracle flips the phase of every state in the superposition. Alright, the argument of structure. The quantum approach can be used to show existence instead of assuming it. When the oracle is applied and we measure, we recover a marked state, or coloring. Simply put, it itself is a proof of construction that structure exists. There's an actual witness, we can say. And also, I want to be careful about what we mean by measure here. As in the quantum sense, it means to collapse a superposition to a specific found arithmetic progression. And marked just means like recorded, or it's found. We caught it. All right, we're basically done. We can have a boost if we would like, quantum speed up. If we consider runtime, classical takes O to the n squared time, and it's n squared since we have to check A, which is, let's say, starting number of the arithmetic progression, and D, its step size. Those are two variables. But quantum has lots of algorithms. We got Grover's, the Deutsch. If we take the Grover's, for example, it can detect a marked arithmetic progression in O of n time due to the square root of a square. So Grover takes the square root of n squared, which is just O of n. And by the way, this O is a different O from Oracle. This O is runtime. This is quantum Van der Waerden theorem. Structure is unavoidable and is now proven via quantum measurement. And after amplification, any measurement yields a valid arithmetic progression, making existence unconditional. And what I mean by amplitude amplification, it just means that we increase the probability of measuring the correct answer. All right, this is our recap. We first initialized n qubits, n being like we established, the minimum number of integers that we satisfied for guaranteed monochromatic progression of length k. Then we use the Hadamard gate on all to the n colorings at once. Next, we apply a phase oracle, which marks states with monochromatic arithmetic progression. This is the key here. And then we measure, which all collapses to arithmetic progression witness. And this shows that structure is guaranteed once we have that witness. All right, now why don't we do some comparison here? Classical Van der Waerden's theorem versus quantum Van der Waerden's theorem. So in terms of methodology, like we said before, classical, it's existential. Like, we just gotta trust that that it's guaranteed for 9 integers, that a length 3 is guaranteed, always. We can't tell if it is, but that's why it's existential. For quantum, we actually created a constructive proof, which is great. Now the search method. Classical, it's just purely combinatorial, whereas for quantum, we used amplitude amplification. When we talk about runtime, classical is O of n squared, quantum is O of n. Structure, classical, it must exist, whereas quantum, the structure is detected. And here's our punchline, because we're mathematicians, we obviously like them. Classical states that complete disorder, not possible, as we said in the first slide. But whereas quantum, order being something that is inevitable. Now these two things are kind of the same thing, but slightly different. Phrasing matters. Keyword being inevitable. All right, let's go through some practicality and challenges. Quantum applications over combinatorial stuff is a real thing, and it's something that a lot of people are doing research on. Amplitude amplification is likely more so proven efficient than classical methods. Here's our issue though. Van der Waals theorem's numbers are just so large. As we said about the 1132 being n, that's crazy. And as we go to higher numbers, we actually face something called quantum decoherence. It's where everything just loses its quantumness. And that is likely more to happen. As well as the fact that our nowadays hardware may not be even able to handle the qubits. But it's nonetheless elegant. But it's just very beyond physical realization at our meaningful scales we have right now. With all this though, it kind of raises a philosophical side to it though. Do we really want to do this? Do we want to pursue this field? Would we want to marshal all the supercomputers? And if so, what's the limit? Like, how far are we going to do this for? Do we want to find all van der Waerden numbers from like maybe 2 to 10? Or could we even tricolor the van der Waerden numbers so we can have a green, which makes our R value 3 now since there's 3? Or we can have a rainbow of colors. And of course, then those numbers would just go insanely high as we consider a higher K or step size. So, but this whole thing really can apply to many things in quantum computing, really. But that is it. I hope you guys enjoyed this presentation on van der Waerden's theorem. And thank you so much to MathQuantum for this opportunity to present. Special thanks to Daniel Serrano for organizing this event, as well as hosting the 2025 MathQuantum High School Fellowship.